All right, so first off, what's coming up around the bend? Today we're doing 4.4. Tomorrow we're doing 4.4, and on Friday we're doing a chapter 4 quiz. Okay, so we have a quiz on Friday over all of chapter 4, all of chapter 4, and then next Monday is a holiday for y'all. We'll review on Tuesday, and we'll test next Wednesday because next week is the last week of this 9 weeks grading period. So we can't test next Wednesday actually because that's going to be PSAT. So we'll have to test on Thursday, right? You'll have the PSAT next Wednesday, so we'll have to test on Thursday. All right. Anyway, we'll deal with that as it comes. Let's go ahead and talk about parabolas. We've been working with quadratics, right? A quadratic is a parabola. A parabola is a very special type of what we call a conic section. Here's a cone, right? Everyone see the cone? It's beautiful. It's like shaded or stained differently for different things here. If you take a plane, like a knife, and you cut through a cone in different angles, if you cut it straight parallel to the base, your cross section will look like a what? What does the cross section look like? It's a circle. Okay, if you cut parallel to the base, you get a circle as a cross section. If you tilt the knife a little bit and you come through one side to the other, you get an oblong-looking circle, which we call a what? An oval is kind of the common name. We actually call that mathematically an ellipse. Have you heard that word? Ellipse? It's an ellipse, but it's really an oval for all practical purposes. If you cut it perpendicular to the base, you get this one right here, which looks a lot like a parabola, but it's not. It's called a hyperbola, and we actually have two of them, one in each direction, okay? But what we're studying here is if you take your knife and you cut it along the side and you come out the bottom at an angle, you get this right here, and that cross-section looks a lot like a what? That's a parabola. So a parabola is really a cross-section of a cone, but it has such amazing properties. We can define gravity, things that are affected by gravity follow parabolic arc paths. When we slow down with our brakes, it's a parabolic curve. But they also have very nice reflective properties. Has anyone ever seen like a football game and there's a guy on the sideline and he's got like a big old dome looking thing with a microphone in the middle? Yeah, you know what they call that? They call that a parabolic microphone. Okay? It's like a big old dish, like a dish on the side of a house, and it's got a little receiver. In fact, those dishes themselves work the same way. Those are parabolic microphones. Okay? The parabola has very, very interesting reflective properties. So if you look at this graph right here, you see the parabola opening up and you see its vertex, right? We can define a parabola to be the set of all points that are equally spaced from a point called a focus and a line called a directrix, okay? So if you look at what I just said, that means that if you draw a line from this point, which is called the focus, to any point on the graph, like that, and then you draw a line straight down to what the line that is perpendicular to the axis of symmetry called the directrix, those two distances are going to equal each other. This distance 1 is going to equal that distance 2. D1 equals D2. They're the same distance. And you could do it anywhere else if you want. If you want to do it right here, you could draw a line to there, and you could draw a line to there. And this distance D1 is going to equal that distance D2. Okay? It's defined to be the set of all points that are equally spaced or equal distance from a point called a focus and a line called the directrix. Now, the distance that we're going to be interested in is the smallest of these distances, which is this right here. That distance right there, we're going to call P. Okay? It's the distance from the vertex to the focus, the shortest distance. And of course, that distance right there is also the same. Okay? But we're going to call that distance P. We call it the focal length. P is called the focal length. Now, here's how those parabolic microphones work. The way that these things work, and is they have beautiful reflective properties, is this. If you have sound coming in like this, you have a parabolic microphone, and you have sound waves that are coming in like this. Any sound wave that comes in parallel to the axis of symmetry, we know the axis of symmetry is the red line. Any sound wave that comes in parallel to the axis of symmetry, when it hits the surface of that parabolic microphone, it's going to be reflected off, and it gets reflected into guess which point? The focus. All of those sound waves bounce off that surface, and they get directed towards that single point. And that's why the parabolic microphone works. You can have a very faint sound off in the distance, But as long as the sound waves come in here, they'll bounce off and it'll get magnified, and the microphone's right there, and that microphone picks up the magnified sound. Has anyone ever been in what's called a whispering room? Like in Washington, D.C., they have this place called the Whispering Room, where it's a huge room with this parabolic ceiling, and you could stand over here on one side of the room, like 50 yards from someone else. You could say, "Hey, that guy over there, he's kind of cute." And guess what? Boom! He's gonna hear it. So be careful if you're in DC in the whispering room, you see a cute guy over there, and you don't want him to know. Because if you whisper it to your friend, he'll hear it over there because it bounces off and goes to the other side. Okay. You also this works in reverse as well. Instead of things coming in, getting bounced to a receiver, a microphone, your headlights work this way as well. If you took apart one of your headlights in your car, you would see that it has a curved background behind the bulb. Okay, the bulb would be right where the microphone is, and instead it's shining out in all directions. And as it shines out in all directions, the light that hits the surface gets what? It gets bounced off parallel to the axis of symmetry, and now you have all of these things going out this direction, and it's called a light beam, right? When they're all traveling in the same direction, you get a light beam. So beautiful properties that the parabola has. The parabola is my favorite of the conic sections. We're not going to study all the conic sections. We're just going to study the parabola, okay? So here's what you need to know about a parabola. If you know where the vertex is, the focus is always going to be on the interior, okay? This again is called the focus, and it's always on the interior. You could think of the parabola as being hungry, and it has teeth, okay? So we'll say this, the parabola eats the focus. The parabola eats the focus. It's always on the interior, okay? And the directrix is always outside of the parabola, and it always runs perpendicular to the vertex or to the axis of symmetry. So in this case, if the parabola opens up, the axis of symmetry is vertical, and the directrix is going to be horizontal. The directrix is always going to be the same distance away from the vertex as the focus is. That point right here, the directrix is always the same distance away as the focus. They're equidistant. That's the definition of a parabola. And it just has a horizontal line, in this case, that runs through it. Okay? So what we're going to do to get an introduction into 4.4 is we're going to sketch a couple of these just so we can orient ourselves with how they open. Because they don't have to open vertically. They can actually open sideways as well. Okay? So let's take a look at this first one right here. On your first graph, if you want to write this down, you can. I don't think this is printed on yours, but you can write it down. We want the vertex to be at the origin, and we want the focus to be at -3, 0. Okay? We're going to draw it. So first things first, the vertex is right here at the origin, and the focus is at -3, 0. 1, 2, 3, -3, 0. Okay? If it's true that the parabola eats the focus, does this parabola open up, down, left, or right? If the focus is on the interior, this has to open this way. We say this one opens left. It opens left. Okay? You can label this as F, you can label this as V. The parabola always eats the focus. Now, if I want to draw the directrix, how do I draw the directrix? Well, what is the distance from the vertex to the focus? How many units was it? It was 3 units to the left. So guess what I'm going to do? I'm going to go 1, 2, 3 units to the right, draw another point, and this time I'm going to draw a line that's vertical. Okay? Like that. There's your directrix. What's the equation of a vertical line? It's x equals. So this would be x equals 3, and the focus is at -3, 0, and the vertex is at 0, 0. Okay? So let's go ahead and answer these questions here. It opens left. Now the p-value, let's talk about the p-value. The p-value is not only the focal length, but it's also what we're going to call the directed distance. Very important. The directed distance, hello, from the vertex to the focus. That is hugely important. The p-value is the directed distance. So distance itself has to be positive, right? Three units this way, 3 units that way. But when we say directed distance, we're turning it into a vector. So to get from the vertex to the focus, I have to go 3 units to the what? Left. So guess what p is? It's not 3, it is -3. Yeah, p is -3. P equals -3. Okay, that's left 3. Directed distance. Okay, what would be the directrix equation? This would be the equation of a vertical line in this case. It's x equals 3. X equals 3. All we need to sketch a graph like this is 2 of these 3 things. I just need to know what 2 of these 3 things. If I know 2 of the 3 things, I can figure out the p-value, and then I can figure out what the other one is. Okay, but if I know 2 of those 3, I plot it, I sketch it, and I can answer the question. We haven't seen a parabola that opens sideways before. This is not a function of x. It fails the vertical line test, but it's still a parabola. Okay, and it still has a focus, and it still has a directrix. Okay, so why is the directrix important? The directrix is important simply because it's part of the definition. When you draw a line from the focus to the parabola, that's going to be the same length as from that point to the directrix. Okay, D1, these are both equal to D1. They both equal each other. For the reflective properties of the parabola, the focus is actually more important. That's how parabolic microphones work. That's how those headlights work. The focus is very, very important. So we focus our attention, if you will, on the focus, and the directrix is almost just kind of an afterthought. Okay, so far so good. We're just drawing these things. All right, the second one. Let's use the second graph here. Write this down. Let's do the vertex at -2, 3, and the focus at 2, 3. All right, so let's plot this. The vertex is at -2, 3, -2, up 3. There's the vertex right there. I'll put a little V by it so I know which point is which. And the focus is at 2, +3. 1, 2, +3. There's the focus. Does this parabola open up, down, left, or right? It opens to the right. We know the vertex, what it looks like. The vertex has to eat the focus. So this one opens to the right. It eats the focus. What's the p-value? Well, let me move my V over here, label it on this side. How far is it from the vertex to the focus? Let's count. 1, 2, 3, 4. It's 4 units. Now, the p-value is the directed distance. So to get from the vertex to the focus, because I have to go to the right, guess what p is? Is it 4 or -4? +4. Yeah, +4. +4. Positive means to the right, negative means to the left if it opens sideways. If it opens up and down, positive means up, negative means down. So keep that in mind. Positive is always up or to the right. Positive is always up or to the right. Negative is always left or down. Left or down. Okay? Now, go ahead and see if you can sketch the directrix and write its equation on your own. Try the directrix. That's a cool name. Directrix. That'd be a cool name for a dog, wouldn't it? Or a human, maybe? Oh, yeah. Feel free to draw and feel free to count. Feel free to use those grid marks to count. I put 6. It's -6. Yeah, sorry. -6. Whoa. Yeah, I counted left. -6. So, again, you go 4 units the other direction. 1, 2, 3, 4. And then you put a dot, and then you draw, in this case, a vertical line through it because it runs parallel to the axis of symmetry. And there you go. You got your directrix. Now let's label the vertex. The vertex is at -2, 3. Let's do one other thing here. What would the equation of the axis of symmetry be? The axis of symmetry would run through here. It would run through those points, through the focus, through the vertex. It would look like that. That's your axis of symmetry. It's a horizontal line. Guess how we write the equation of a horizontal line? Not x equals, but what? Y equals. And what's the y value that it passes through? 3. Yeah. So the axis of symmetry is y equals 3. It's all about drawing these things. If you could draw it and you can kind of get your terminology straight, your definitions, then you're in good shape. Directrix is always the line. It doesn't intersect the parabola. It runs the opposite direction or parallel, perpendicular, I should say, to the axis of symmetry. And the p-value is always not just the distance, but the directed distance from the vertex to the focus. All right. You try this one on your own. I'll let you do the whole thing on your own. I'm going to do it quietly up here so we can compare answers. Okay? On your mark, get set, go. No help from me. Plot your points. Know that the parabola eats the vertex, or the focus, sorry, the parabola eats the focus. So you get it. It looks like this: 0, -4, 5, -4. So if you eat the focus, it opens to the right. The p-value is the directed distance from the parabola itself, from the vertex to the dot, which is 5 units. So because it's to the right, p is +5. If you go back 5 units, then 1, 2, 3, 4, 5, you're at -5, and that's the vertical line. Then x equals -5. That is the directrix. We actually draw the directrix as a solid line, not as a dotted line, because it is a solid line. It actually exists. It has to be there if we're going to use the definition that it's the same distance from the focus to the parabola as it is from the parabola to the line. The axis of symmetry we draw as a dotted line because it's an imaginary line that we would fold it across to get it to line up with itself. So if you're wondering why I did one dotted line and one solid, the axis of symmetry, if we throw that in there, that's just going to be the y coordinate in this case of the vertex. Y equals -4. All right, so we've seen 3 parabolas now that open sideways. Let's try the next one. Let's do this one together because it's a little bit different. Now it tells us the vertex is at 3, 2. 1, 2, 3, 1, 2. So there is your vertex. I'll label it as V. And the directrix is at y equals -1. So here's y equals -1. It's nice to be able to snap a line. Y equals -1. Which way does this parabola open? Up, down, left, or right? Up, right? Very good. If the parabola eats the focus, it always is repelled or goes away from the directrix. So if I were to draw that going left, right, or down, it would intersect the directrix, and it doesn't. It never intersects the directrix. So you can draw your parabola going up like this, up like that. Now let's count. How far away is it from the vertex to the directrix? It's 1, 2, 3. This distance right here is 3 units. So what should the p-value be? Good. It's positive 3 because it opens up. I would have to go 1, 2, 3 right here, and that would be the point 1, 2, 3, 1, 2, 3, 4. That would be the point 3 comma 5. Yeah. So P is positive 3. And then your focus, we said, is 3 comma 5. And then what is your axis of symmetry going to be? Your axis of symmetry is now the vertical line that runs through the vertex. What's the x coordinate of the vertex? 3. Yeah. So the axis of symmetry is always going to involve the vertex. If it's a vertical axis of symmetry, it's x equals the x coordinate. If it's a horizontal axis of symmetry, it's y equals the y coordinate. All right, so that's one like we're used to. It opens up. It's a function of x. It passes the vertical line test. All right. Well, she gave us quite a few to work on here. Let's try this one together. Y'all do this one by yourself then. So we've already seen the directrix. Y'all do this one. I'll do it myself quietly, and we'll compare answers. Right now, it doesn't matter how wide you open your parabola, as long as you just kind of have a parabola going out that direction. In order to preserve the distances, though, from the focus to the parabola and the parabola to the directrix, that actually determines how wide it opens. But we're not going to be too picky about that right now. If we can get it to open the right way and we can figure out that focal length, we're in good shape, as long as we draw it. Drawing is the key, right? Drawing is the key. So this one, vertex is at negative 4, 0. The directrix is 2 units to the left of that. So that's a vertical line. X equals is a vertical line. The vertex is at negative 4, 0. So the focal length is 2 units not to the left, but 2 units to the right of the vertex. So P is positive 2. And the focus then is at negative 2, 0. The axis of symmetry, which I drew through the vertex and through the focus, is going to be y equals the y coordinate of both of those, which is the 0. Y equals 0, the x-axis. Pretty neat. You got to love the parabola. My favorite conic section because of its reflective properties. It's beautiful. Um, okay, last one here. Go ahead and do this one on your own as well. Let's. We haven't seen one that opens down yet, but that's okay. They exist. They do exist. We've seen a lot that open horizontally, simply because we're not used to seeing them horizontally. She gave us more examples. She being Coach Richter, she sent this to me. She's the algebra 2 boss. Carefully counting. All right, so hopefully you got that. Let's summarize about P. If P is positive, that means greater than 0, then the parabola is going to open up or right. Yeah, either one. Up or right. That's the positive direction on the coordinate plane. If you want to get bigger, go in the positive direction on the coordinate plane. You either go up or you go to the right. If P is less than 0, which means if it's negative, it's going to open one of two directions. It's going to open down, which we haven't seen one of those yet, but it does. They exist. Or it's going to open to the left. So the sign of P, the directed distance, tells you which way it opens. It's pretty nice. Okay. Any questions on the terminology, what they are? And again, just to reinforce the definition, mine is not drawn correctly, but we're saying that the distance from the focus to here is the same as the distance from here to here, which you can see that those aren't actually equal to each other, right? The way I sketched it. But in the real parabola, those would be equal to each other. In order to make those equal to each other, I would have to make my parabola a little bit wider, narrower or wider to make these equal to each other. I'd have to make it what? A little bit wider. If I made this a little bit wider, then this distance getting a little bit bigger, that's getting a little bit smaller. So that's how the aperture of the parabola is controlled. How wide or how narrow it is by the definition that they have to be equal. So when we sketch it, we don't really concern ourselves with drawing it perfectly to scale, but we know that those are supposed to be equal. We do know that this equals this, right? And that's important. That's the P value. P equals P. Or I should say the absolute value of P equals P. Okay, let's go to the notes then, the real notes. 4.4, number 3. I've already talked you through all that. Here's kind of a summary of what they look like. The only thing that's different here is the format. So let's look at these two equations right here. This is the standard form for the conic section. We call this conic form. Instead of vertex form, we call this conic form. Let's write that in here. Conic form. What is conic form? If it opens up or down, either one, if it opens up or down, we still have our x being squared, right? We're used to seeing x squared. If it opens up, x squared is positive. If it opens down, x squared is negative, right? So if it opens up, we're still used to seeing, we're still seeing the x squared. But we isolate the x squared piece, and we let everything else go to the other side. And so this is the form we're looking for. X minus h squared is equal to some number, which we're going to call 4p times y minus k. Now, why is that significant? This is also the vertex form and conic section form. The vertex is at hk still. X minus h, y minus k. It's now the opposite of what it appears to the inside as well, because it's inside the parentheses. So the vertex is at hk. But the number in front of the non-squared term, that's going to equal 4p. And if I know what 4p is, I can figure out what p is just by dividing that number by 4. And once I know what p is, I can actually sketch it. So if it opens up or down, we isolate the x squared. If it opens side to side, it looks like this. It's y minus k equals 4p times x minus h. The vertex is still at hk. We still associate the h with the x, k with the y, and then 4p is over here. So that's if it opens sideways. If p is positive, of course, it opens to the right or up. If p is negative, it opens to the left or down. So these are the only two things that we need to concern ourselves with. Isolating the squared piece, getting the vertex, and finding p. Okay? Let's see if we can do that. Instead of being given information, let's see if we can be doing it with either writing an equation or graphing it the same way. So here's example 1. Write the equation of the parabola. So our goal now is to end up with one of these two equations. Okay? And they're giving us part A vertex at the origin and focus at 0, -5. This is exactly what we just did. Let's draw it. Let's identify the key features. And then we'll take our ingredients that we have out in front of us, and we'll just assemble them into the right equation. All right, vertex at the origin, so that's going to be right here at 0, 0. That's my vertex, V. The focus is at 0, -5. So 1, 2, 3, 4, 5. There's my focus. And so now we know if the parabola eats the focus, this thing opens what? It opens down, like that. Okay? This distance here is 5 units. So what should P equal if we're going down 5 to get there? -5. Fantastic. Y'all are fantastic. That's -5. And then for what it's worth, the directrix, if I go back 5, the opposite direction, 1, 2, 3, 4, 5, that puts us right here. The horizontal line that runs through that point is going to be at y equals 5. This distance here is also 5. But P is -5 because it opens downward. Okay, so here's what we're going to do. Because it opens vertically, we're going to use this one over here. This one is for the vertical opening. All right, so I'm going to bring that down here, and I'm going to write the template. It's x minus h squared equals 4p times y minus k. There's my template. All right, what do I do with the template now? Well, I plug in. Do I know the vertex? Let's see. The vertex is at 0, 0. So what is h? 0. And what is k? 0. And what is p? -5. That's really all we need to know to plug into here to get my equation. I need to know h, I need to know k, and I need to know p. So let's carefully plug in. I get x minus 0 squared equals 4 times -5 times y minus 0. And technically that's the equation. Okay, that's in conic form right there. If we don't simplify, that's in conic form. And we've met the requirements. Let's see if we can simplify that a little bit though. That's just x squared over here. That's going to be -20 times y. Now because this one opens vertically, we can actually solve it for y like we're used to by dividing through by -20, and we get -1/20 x squared. I just solve for y. Divide through by -20, and I get -1/20 x squared. This is going to be in your standard form. Now, standard form is great. If I gave this to you walking in the door today, and I said, please sketch that, y'all would do this. You would be like, oh, it's x squared. It's not left, right, up, or down, so the vertex is at the origin. It's a -a value, and it's 1/20, so it's going to be a vertical compression, so it's going to be pretty wide, and it's going to open down. Y'all draw it like that, which is great for knowing what the parabola looks like. But guess what information is lost when it's in standard form? We don't have the p-value. There's no way to know how far we go. We know the focus is over here somewhere, but we don't know what that distance is. That's why we don't like standard form if we're interested in getting it into the conic form, all right? So what would be the acceptable equation if you wanted to stop? You can stop right here. That's typically where we're going to stop. If you left it in this form, it would be x squared equals -20 times y. That's the simplified conic form, but it's still conic form. Those all mean the exact same thing. Yeah, they're just different forms. Because we're in conic section form, this line right here is equivalent to this line here. This would be your answer if you were typing it in somewhere. We're isolating the squared piece. Now, because it opens vertically, I could solve it for y, and I just did that so you can recognize it. You're like, oh, that's just the same equation. This equation and this equation are exactly the same. They're just slightly in different forms, right? One of them is more useful for certain things, and the other one's more useful for other things. This last one here in standard form is very useful if we're just interested, bless you, in a sketch of the parabola, whether it opens up or down. But if I'm interested in its reflective properties and I want to know where the focus is, I want it in this form right here so that I can be staring at this. This -20 is equal to 4p. Like if I gave you that equation right there, let's say I gave you this equation and I asked you what the focal length p is, you would say, oh, the number in front of the non-squared term, -20, that equals 4p, right? It always equals 4p. So how would we solve for P? We would divide by 4 and we get -5. And now you're like, oh, okay. Now I know the focal length is 5 units downward. So I know exactly where to place the focus. Okay. Let's try the next one together. Letter B. The vertex is at 3, -1, and the directrix is at -1. Okay, step 1 is to sketch the graph and get all of our information laid out in front of us. So 3, -1. 1, 2, 3, -1. There it is. There is the vertex. I'll label it as V. And the directrix is x equals -1. So that's going to be, that's your vertical line that runs through x equals -1. It looks like that. Does this one open to the left or to the right? Yeah, it opens away. It either eats the focus or it goes away. It's repelled by the directrix. So it's going to open this way. It's going to open that way, away from the directrix. Now, we don't know where the focus is yet, do we? So let's count. How far is it from the vertex to this closest point on the directrix? 1, 2, 3. It's 4 units. So from the vertex, I go 4 units more. 1, 2, 3, 4 to here. And now I have my focus. So what is P? Is P 4 or -4? 4. Yeah, remember, if it opens to the right or up, P is positive. If it opens to the left or down, P is negative. So really all I need is my vertex. Let's put it right here. The vertex was given is at 3, -1. All right, I'm going to copy this information because I get tunnel vision. And I'm going to bring it over here. Now, because it opens horizontally, here's your horizontal conic form. Your horizontal conic form is going to be y minus k squared equals 4p times x minus h. We're not used to seeing the equations of a parabola that opens sideways. We're used to seeing y equals x squared, right? Y equals x squared. That either opens up or y equals -x squared opens down. But when the y is squared and the x is not, that's the opposite from what we're used to seeing, right? We're not used to seeing x equals y squared. That's your trigger that's going to be the equation for the one that opens sideways. When y is squared and not x, it opens sideways, okay? So we're going to use this as our form. Well, now it's just a matter of dropping in the h and the k and the p. So here we go. The equation in horizontal conic form is y minus k. This is your h and this is your k. So what's y minus -1? +1 squared equals 4 times p, which is 4, times x minus 3. And if we simplify that, we get y plus 1 squared equals 16 times x minus 3. That is your equation in conic form. You don't have to solve for x. I only solved for y in the previous one so we can recognize it in the other form. We're isolating the squared piece. 4p is in front, x minus 3. Now, if I gave you this equation and I asked you for the p-value, you would just say, oh, the number in front of the non-squared is 16. That's 4p. Set 16 equal to 4p. Solve for p and you get p equals 4. Okay? So we should be able to go both ways. Write the equation, or given the equation, we should be able to sketch the graph. All right. That's just a summary of everything that we've done. If you want to read that, you can. Let's go the opposite direction now, shall we? This is the first time we're doing this, the opposite direction. We'll stop after this one, okay? Identify all the information for this parabola. X plus 5 squared equals 12 times y minus 1. Okay, first of all, does this one open horizontally? Or does it open vertically? Vertically. Okay, good. How do we know it opens vertically? X is squared. That's what we're used to seeing, right? We're used to seeing x squared. When it's y equals x squared, it opens up. When it's y equals -x squared, it opens down. So if you see the x squared and the y is not, that opens vertically. Okay, cool. So I know it opens either up or down. Now, once we do that, I need to find p. So the number in front of the non-squared, which is 12, I'm going to set that equal to 4p. Every time you set it equal to 4p. Every time you set it equal to 4p. Every time you set it equal to 4p. And you solve for p and you get 3. So now I know not only does it open vertically, since p is positive, it actually opens what? Up or down? Up. Okay? Positive is up, negative is down. So we're knowing a lot about this already. It's a parabola that opens up. Okay, cool. Do we know where the vertex is? Tell me where the vertex is. -5, +1. Yeah, because they're both in parentheses now, they're both the opposite of what it appears. I know that's kind of strange, but they're both in parentheses now, so they're both opposite. So it's -5 and +1. -5 and +1. That's HK. All right. Is that enough to sketch the graph? I think so. Let's go to the vertex first. -5, 1. 1, 2, 3, 4, 5. And then +1. There it is. There's your vertex. And then the focus is 3. So from there, I'll go up 3, 1, 2, 3. And then I'll go down 3, 1, 2, 3 from there. And then I'll draw my directrix like this. And if you forget, you can just count. That's at y equals -2. And then the 1, 2, 3, 4. This is at the focus is at -5, 1, 2, 3, 4. So let's go ahead and write. Let's write the value of p is 3. The vertex is at -5, 1. The directrix is at y equals -2. The focus, if we count, we can actually just count the dots. Left 5, up 4. Or you can actually add it to the 1 there, but it's easy just to count. It's -5, 4. Let's go ahead and draw the parabola. I haven't even drawn the parabola yet. It doesn't really matter. We know it eats the focus. The axis of symmetry would run this way through the focus and the vertex. And because it's a vertical line, it's x equals what? X equals -5. And then the directrix, the last thing. Ooh, the direction. I'm sorry. I didn't read that carefully. The direction is up. Yeah, opens up. And the directrix is y equals -2. So again, we should be able to go either direction. If I give you the equation, you should be able to sketch the graph. If I give you the graph, you should be able to collect your information and drop it into the form to create the equation. Back and forth and back. How does that feel so far? All right, I'm going to save the last one for tomorrow so that we can, we are going to have to complete the square. Oh, yucky, yucky, gross, gross. Okay, that's it. So again, the reflective properties of parabolas. Look for them in your everyday life. Look at those headlights next time. When you get home, get in front of the garage door, turn your lights on, and look to see the beam that's pointing right there at your garage door. Imagine all those light beams are coming out parallel as they reflect off that parabolic mirrored surface behind the bulb that's in your headlight. That's the power of the parabola right there. Or look up parabolic microphone, and you'll see a guy just standing on the sideline at a football game. Let's actually do that together. If you want to turn your calculators in, parabolic microphone. There he is. There's the guy standing on the sidelines. Have you ever seen that guy? He's trying to intercept the plays that are being called in the huddle, right? Or he wants to know if the guys on the field think he's cute. What? What did he say? You've never seen that? Not at a high school football game. This is all the time at professional football games. Yeah. College or professional, yeah. Look for them. They don't really show the sidelines much, but there's usually a guy somewhere on the sidelines with one of those. Parabolic microphone. He's doing espionage work. That's what he's doing. Okay? All right. Any comments or questions on today? You like parabolas? As much as I do? Not yet? Not yet.